Hi, welcome back to this first video talking about synchronous communication, the famous used ways and technologies to implement it, and their main challenges. This course tries to help you choose and use some specific technologies to implement the synchronous remote procedure invocation pattern. The remote procedure invocation is a synchronous style of communication widely used to make microservices communicate. When using a remote procedure invocation-based IPC mechanism, a client sends a request to a service, and the service processes the request and sends back a response. Some clients may block waiting for a response, and others might have reactive non-blocking architecture. In both cases, the client assumes that the response will arrive in a timely fashion. We are implementing here one-to-one synchronous communication, the famous request-response interaction style. Actually, the remote procedure invocation pattern works as follows. The business logic in the client invokes a proxy interface implemented by a remote procedure invocation proxy adapter class. The remote procedure invocation proxy makes a request to the service. The request is handled by a remote procedure invocation server adapter class, which invokes the service's business logic via an interface. It then sends back a reply to the remote procedure invocation proxy, which returns the result to the client's business logic. To implement the remote procedure invocation pattern, there are numerous protocols and technologies to choose from. In this lecture, I chose to talk about the two most used and famous ones, REST and gRPC. But if you are interested in knowing much more about the other existing open source projects, I advise you to check the remote procedure call section of the CNCF interactive landscape. You can find the link in the video description. So let's begin first with REST. Today, it's fashionable to develop APIs in the RESTful style. In this video, I will not explain the concept in depth, since this is not the purpose, and since nowadays almost all the developers already know and use REST to develop web applications. However, if you want to get a deeper idea on it, you can check the link I put in the description, in which you will find the PhD dissertation of Thomas Fielding, the guy who is behind REST. REST, which stands for Representational State Transfer, is an IPC mechanism that almost always uses the original specifications of HTTP. So REST is not a new technology, it is an architecture style that defines a set of constraints. A system respecting these constraints is described as RESTful. Before talking about these constraints, I will first give a kind and brief overview of the key concepts of RESTful services. A key concept in REST is a resource, which typically represents a single business object, such as a customer, a product, or a collection of business objects. REST uses the HTTP verbs for manipulating resources, which are referenced using a URL. For example, a GET request returns the representation of a resource, which is often in the form of a JSON object or an XML document, although other formats such as binary can be used. And the other verbs are post request, which creates a new resource, the put request updates a resource, and the delete request deletes it. Back to the REST constraints, the original constraints are actually 5. The first one says that the system has to respect the client-server architecture. The second says that system has to be stateless, which means no session information is retained by the server. The third constraint allows clients and intermediaries to cache some responses. The first one says that the system has to be layered, which means that the system can have some intermediary servers such as load balancers and proxies, which can call multiple other servers to generate a response to the client. The fifth and last constraint is the uniform interface, which is composed of 4 other constraints. The first one is the resource identification in requests using unique resource identifiers. The second is resource manipulation through representations. The third is self-descriptive messages that have to include enough information to describe how to process the message. And the fourth is the hypermedia as the engine of application states, also known as HATEOAS. Each of these constraints affects many architectural properties of the system and its components, such as the performance, the scalability, the visibility, the portability, the reliability, and many others. So don't forget, you can find more information about REST in the links I shared in the video description. Many developers claim their HTTP-based APIs are RESTful, but unfortunately, not all of them actually are. To understand why, let's take a look at the REST maturity model defined by Leonard Richardson, and that consists of the following levels. The lowest level of the model describes a web API with a single URI unified resource identifier, which is typically a post over HTTP, accepting all the range of operations supported by the service. Resources in this form cannot be well defined. Messaging is done in XML, JSON, or other text formats. These are similar to what we typically call RPC plain old XML, or the POX for brevity, to mention that level 0 systems are not classified as RESTful. A level 1 service supports the idea of resources. It allows to make requests to individual URIs, still all typically post verbs, for separate actions instead of exposing one universal endpoint. The API resources are still generalized, but it is possible to identify the scope of each one. Level 1 design is not RESTful, yet it is organizing the API in the direction of becoming one. A level 2 service uses HTTP verbs to perform actions: the get to retrieve, the post to create, and put to update. The request query parameters and body, if any, specify the actions parameters. This allows to further specialize the resource and thus narrow down the functionality of each individual operation with the service. In addition to that, this enables services to use web infrastructure such as caching for GET requests. One drawback of providing a distributed service with more than GET and POST per resource may be growing complication of using such a system. The design of level 3 service is based on the HATEOAS, the hypertext as the engine of application state principle. The basic idea is that the representation of a resource returned by a GET request contains links for performing actions on that resource. For instance, a GET request to a hotel reservation system might return a number of available rooms along with hypermedia links allowing to book specific rooms. The benefits of HATEOAS include no longer having to hardwire URLs into client code. And this is the last level of the resource maturity model. At the end, I encourage you to review the REST APIs you already produced to see which level they correspond to. You can also read more about this REST maturity model and the benefits of corresponding to the third level by reading the blog post I shared in the video description. As mentioned in the previous video, you must define your APIs using an interface definition language. Historically, REST didn't originally have an ideal. Fortunately, the developer community has rediscovered the value of an ideal for RESTful API. The most popular REST ideal is the Open API specification, which evolved from the Swagger open source project. The Swagger project is a set of tools for developing and documenting REST APIs. It includes tools that generate client stubs and server skeletons from an interface definition. REST resources are usually oriented around business objects. Consequently, a common problem when designing a REST API is how to enable the client to retrieve multiple related objects in a single request. For example, in a blogging application, an app needs to display the titles of the posts of a specific user. The same screen also displays the names of the last 3 followers of that user. How would that situation be solved with REST? A pure REST API would require the client to make at least 3 requests. The first for the initial user data, the second for all the posts for a user, and the third for a list of followers per user. A more complex scenario would require even more round trips and surely suffer from excessive latency. One solution to this problem is to follow the REST client retrieving related resources when it gets a resource. This solution may work well in some situations, but it is often insufficient for more complex scenarios and it's time-consuming to implement it. This has led to the increasing popularity of alternative API technologies such as GraphQL and Netflix Falcor, which are designed to support efficient data fetching. For example, in GraphQL, you'd simply send a single query to the GraphQL server that includes the concrete data requirements. The server then responds with a JSON object where these requirements are fulfilled. Another common REST API design problem is how to map the operations you want to perform on a business object to an HTTP verb. A REST API should use put for updates, but there may be multiple ways to update an object, including canceling it, revising the object, and so on. Also, as a requirement for using put, an update has to be idempotent, which means getting the same response no matter how many times you request it. This criteria is not guaranteed if you use a wrong way to make an update. It's possible to find a way to unblock the situation, but the problem is that all the options you may do could not be RESTful. This problem with mapping operations to HTTP verbs has led to the growing popularity of some alternatives to REST that works differently, such as gRPC, which I will introduce further in this video. Using REST has numerous benefits. For example, it is simple and familiar. You can test an HTTP API from within a browser using, for example, the Postman plugin or from the command line using curl, assuming JSON or some other text format is used. REST directly supports request-response communication style. HTTP is, of course, firewall-friendly, and REST doesn't require an intermediate broker, which simplifies the system's architecture. On the other hand, REST has some drawbacks too. For example, it only supports the request-response style of communication. Reduced availability is another problem because the client and service communicate directly without an intermediary to buffer messages, and they must both be running for the duration of the exchange. Clients must know the locations, the URLs of the service instances. This is a non-trivial problem in a modern application. Client must use what is known as the service discovery mechanism to locate service instances. As seen a few seconds ago, fetching multiple resources in a single request is challenging, and it's sometimes difficult to map multiple update operations to HTTP verbs. After briefly introducing the REST architecture style, let's get an idea on gRPC, the lightweight binary-based RPC communication protocol brought out by Google. gRPC was thought as an alternative to REST, which generally used JSON or XML over HTTP. The problem with this traditional approach is that service A has to encode its data into JSON, for example, send a large string over the wire to service B, which then has to decode this message from JSON back into code. Actually, this has potential overhead latency problems at scale. So whilst we are forced to adopt this form of communication for web browsers, services can just about talk to each other in any format they wish. And this is the main idea behind gRPC. In gRPC, a client application can directly call a method on a server application on a different machine as if it were a local object, making it easier to create distributed applications and services. As in many remote procedure call systems, gRPC is based around the idea of defining a service, specifying the methods that can be called remotely with their parameters and return types. On the server side, the server implements this interface and runs a gRPC server to handle client calls. On the client side, the client has a stub, referred to just a client in some languages, that provides the same methods as the server. gRPC clients and servers can run and talk to each other in a variety of environments and can be written in any of gRPC's supported languages. So, for example, you can easily create a gRPC server in C++ or Java with clients in Go, Python, or Ruby. gRPC uses binary as its core data format. In RESTful services using JSON, we would be sending a string over HTTP. Strings contain bulky metadata about its encoding format, about its length, its content format, and various other bytes of pieces. This is that a server can inform a traditional browser-based client what to expect. We don't really need all of this when communicating between two services, so we can use cold hard binary, which is much more lightweight. In addition to that, gRPC used the new HTTP2 specification, which allows for the use of binary data. It even allows for bidirectional streaming, which is pretty cool. HTTP2 is pretty fundamental to how gRPC works. So by default, gRPC uses protocol buffers as both its interface definition language IDL and as its underlying message interchange format. Protocol buffers are language neutral, platform neutral, extensible mechanism for serializing structured data. We specify how we want the information we are serializing to be structured by defining protocol buffer message types in those proto files. Each protocol buffer message is a small logical record of information containing a series of name value pairs. Then we use Proto-C compiler to generate data access classes in our preferred language from our proto definition. After that, we implement the gRPC client and server. gRPC has several benefits. It is straightforward to design an API that has a rich set of update operations. It has an efficient, compact IPC mechanism, especially when exchanging large messages. Bidirectional streaming enables both RPI and messaging styles of communication. It enables interoperability between clients and services written in a wide range of languages. gRPC also has several drawbacks. For some programming languages, it takes more work for clients to consume gRPC-based APIs than REST JSON-based APIs. Also, older firewalls may not support the HTTP2. So gRPC is a compelling alternative to REST, but like REST, it is a synchronous communication mechanism. So it also suffers from some problems that I will cover in the next two videos. To sum up, here are the key ideas to remember. One evident and easy IPC option is using the synchronous remote procedure invocation pattern. The remote procedure invocation pattern can be implemented using different communication technologies, including REST as a de facto. The REST architecture style has a lot of benefits and at the same time, a lot of challenges to overcome. Thus, many other projects appear to overcome such problems. The most famous nowadays are GraphQL and gRPC. In their turn, each of these technologies has different trade-offs. That's it. Your questions are welcome. Don't forget to subscribe to the channel. See you in the next video.